All right, good morning, everyone. Welcome to the inaugural Spark Summit in Amsterdam. Today we'll be doing exploratory data analysis on various Wikipedia datasets using Apache Spark. Imagine a world in which every single person on the planet is given access to the sum of all human knowledge. That's what Wikipedia is trying to do. It was created in 2001, currently about 35 million articles in 290 languages. There are 67,000 active contributors to Wikipedia. This is just for the month of September 2015. And 374 million unique visitors per month. This is also very recent for September 2015. And all of the Wikipedia corpus has been open sourced under a Creative Commons license. So in this class, we're actually going to focus on just the English Wikipedia, which currently has close to 5 million articles. It is actually at about 4.99 million articles as of this morning. And I anticipate it will hit 5 million any day or any hour now. It's roughly 50 to 60 gigabytes of data, and the English Wikipedia has about 30,000 active contributors. Now, this is a snapshot of English Wikipedia, if you got the current live snapshot. But as you may know, Wikipedia is built by community editors. And if you go back and trace the origins of Wikipedia to 2001 and try to rebuild it with all of the edits, then it is about 10 terabytes of text uncompressed and 100 gigabytes compressed. So to give you a sense of how big the current snapshot of English Wikipedia is, once again, as of this morning, it's roughly 2,211 volumes. So there is a kind of a person standing there on the left. This is 12 different stacks of books. And once again, this is English Wikipedia without images and without edits. So we will be analyzing Wikipedia with Apache Spark, which began as a research project at UC Berkeley's AMP Lab in 2009. It is also an open source project under the Apache 2.0 license. The latest stable release is 1.5. It is about 600,000 lines of code, of which 75% of it is Scala, built by close to 1,000 developers from 200 companies. And it is currently the most active open source project in data processing period. The goal of Apache Spark is to be a unified engine across data sources, workloads, and environments. So let's take a look at the workloads that Apache Spark can process. There's Spark Core for batch analytics, above which are higher level libraries to do SQL queries, streaming analysis, machine learning, and graph processing. And all of this is accessed via two APIs, the data frames or SQL API, or the lower level RDD API. And there are bindings to both of these APIs in 4 languages, in Scala, Java, Python, and R. We'll spend most of today in Scala. So the data sources that Spark can read of are many. Here are some of the most popular. There's relational databases, NoSQL columnar databases like Cassandra and HBase, distributed file systems like HDFS, there's Hive, JSON, CSV readers, Elasticsearch, Amazon S3, which is actually where most of today's data sets live. Parquet files can be read, and so can live streams through Kafka. and the environments it supports are various as well. So what does a Spark physical cluster look like? Well, Spark is made of a bunch of JVMs. There's a driver JVM that you can think of kind of like the brain of your cluster. That's where the command control center of Spark is. And then there are a bunch of executor JVMs that live out on your worker nodes. And you can see that the executor JVMs have slots on them, and on those slots, tasks can run. And this is how you distribute the computation. So I work at Databricks, and we are the company behind Spark, founded by the creators of Spark in 2013, and we contributed 75% of the code to Spark in 2014. I personally work in the training department of Databricks, and if you are interested in learning more about our training offerings, then please check out this link. So the agenda for today, as seen through the perspective of today's labs, first we'll spend about an hour exploring the data frames API. Particularly, we'll look at the Wikipedia page views per second data file, which is about 255 megabytes. After that, we'll move into a larger data set, the clickstream data set, that now approaches close to a gigabyte. And we'll analyze the clickstream using data frames and SQL. We'll do lunch. And then we will tackle the actual snapshot of English Wikipedia using RDDs and data frames. We will then revisit the clickstream data set, but this time from the GraphX library. And then finally, we will connect to the live edit stream of Wikipedia and do some analysis on that. So I expect today to be about 30% slides and 70% live coding, demos, or hands-on labs. And here are some guidelines to make sure we all get the most out of today. There are roughly 100 people in the room here, so I would like to ask you to keep Q&A low. This is because I have a lot of material I would like to cover, and I think this is how you'll get the best out of today, the most out of today. I will hang around, though, at 5 o'clock for about 20 minutes to take any questions you have. So this day is being live streamed on YouTube. And after today, maybe a few weeks from now, this recording will end up on YouTube as well. So don't worry about taking like diligent notes or anything. The video will be online. I'm going to ask you guys to do a feedback survey around 4 p.m. We'll take 2 or 3 breaks. We'll take 1 break at approximately 10:30. We'll do lunch at noon. And we'll take another break after lunch, maybe like an hour after lunch, and then perhaps another one an hour after that. Now, one thing I would like to ask today is don't get caught in the details of what I'm going to show you. Try to instead focus more on the higher picture, the broader intuition I would like you to get for what Spark is capable of. I'm going to move fast and go through a lot of things. So what I'm trying to say is if I show you some sample code, don't try to really understand perhaps its syntax if you're not very familiar with Scala. Instead, try to get a sense of what it's capable of. OK, so let's start by this. I would like to ask for a show of hands if you have edited Wikipedia before. Wow, OK, so that is about 20% perhaps of the audience. So let's go and get right to it. Let's start analyzing the page views per second data set. So Wikipedia is one of the most heavily trafficked websites in the world. It is actually the only nonprofit in the top 10 global websites list. Here is what the page views data set looks like. So we're going to look at this in lab, but I wanted to introduce you to what it looked like first. So I'm displaying a data frame here. that is called the page views data frame. And you can see 3 columns, a timestamp column, whether the request was for mobile or desktop, and how many requests came in. So this data is timestamped per second. So every second, we're actually getting 2 rows, one for desktop and one for mobile. And this is very recent data, actually. It's from March. It starts March 16th, 2015. And then every second, we get 2 rows for the next 41 days. Now, you can see, actually, that this data is out of order, it appears. You can download this data from this link at the bottom. It has been made available for analysis by the public by the Wikimedia Foundation. And one of the questions that we're going to try to answer this morning is this. On a given day of the week, do more people access Wikipedia via a desktop computer or a mobile computer? So at Databricks, we have a philosophy or a mission statement that simple things should be simple and complex things should be possible. So we'll be doing some of the simpler things this morning and some of the more complex things this afternoon. So I'm now going to switch to a live Databricks environment. And you're welcome to follow along with what I'm going to do now. I'm basically going to walk you through some of the Databricks user interface, and then through also some portion of the first lab for today. So when you log into Databricks, you'll be presented with this screen. You can click here to see any new features. You can create notebooks, create clusters. So you usually want to start your Databricks experience by clicking the Navigator button. And we can see many different things here, many different options. We'll spend most of our time in the workspace, in which you'll see a labs folder, under which you will see a Wikipedia table of contents folder. So that's what I'm looking at here. And Databricks has a bit of a collaborative nature to it. So it's kind of like Google Documents. When multiple people are editing the same document, I can see actually there's a bunch of other people who have entered this specific document. If I click on this, it takes me to a locked version of this notebook that is not editable. But you can kind of scroll through it and read it. But how do you actually make this notebook come alive so you can edit the code? Well, to do that, you will want to not go to the static locked copy, but instead go into the private users folder. And in there, you'll find your own home folder. I'm actually going to go to my home folder here because I'm an administrator. I'll go to labs, and then I'm going to go to the first lab. And here, I'm going to expand this by moving this little thing here. And I'll go to the Run Me version of page views. So you might have noticed there were 2 versions of page views there. Let me make this a little smaller. OK, so there's a README version and a Run Me version. The README version is meant for those of you who don't really want to perhaps do live coding, but you just want to skim through some of these sample notebooks. And you can see that the output is already in the README version. So this version reads more like a book. However, if you want to execute the commands before you see the output, then you'll want to go to the Run Me version. And in this one, you'll notice that actually there is no output. So you have to execute the cell. Now, to execute the cell, actually, you'll notice that if I try to go into this cell and I hit Shift-Enter to execute it, it gives me this like a warning message saying that I'm not attached to a cluster. So before I attach to a cluster, let me show you what the clusters look like. So I'm going to go down here to the clusters menu. And well, if I scroll down, there's actually many clusters running here. Every one of you has your own cluster. So the first thing to keep in mind is please make sure you attach your notebooks only to your cluster. So I also have a larger cluster here, kind of a community cluster with 8 worker machines in every shard. We have 3 shards actually here today. So there's AW, which stands for Advanced Wikipedia, and then 02, there's 01, and there's 03. All right, so you'll be on one of these 3 shards. And under there will be somewhere between 10 to 50 clusters launched, one of which will be called the 8 workers cluster. Now, this one is a community cluster, so if you want to scale up your workload, you're welcome to attach to this cluster. However, beware that other people might be attached to it as well. So your job might be delayed as previous people's jobs are being processed. But if you attach to your own cluster, then only you get access to that cluster. So you should be have a more predictable experience if you attach to your own cluster. So let's go back to the notebook. So I will go to the users folder, and then admin, because that's who I am, and then labs, 1, and then once again, if you can't really see which one is readme or runme, just kind of scroll this over, and I can tell that this is the runme, and I want to run the command, so I'll do that. And then I will attach to my demo cluster. And in just a moment, I should see that this notebook will be attached. There we go. Now, let me show you what is in the menu up here. If you go to File, there's a few things you can do. You can rename this folder or this notebook. You can, most importantly, you can export it. You can export it out as HTML. Or you can get the source file. This is a Scala notebook. So I can get actually the raw Scala in here. And then I can export out this notebook and run it, perhaps run the code on-premise in my own Spark cluster if I want to. Or I can export it out as a Databricks archive, and then I can import it perhaps into my own personal Databricks account if I want to. OK, so that's all for now. Let's start looking at what we're doing in this lab. So the way I'll do this is I'm going to walk you through maybe about 20 to 30% of this notebook, and then I'll have you play around with it for a little bit on your own. And then I'll come back and kind of do a live demo of the rest of the notebook. So this is a good time to go ahead and launch your own version of this notebook up so you can perhaps follow along. So remember, once again, you're just going to go to the Navigator button, go to the private users folder, find your own user folder. There should be a labs folder in there. Go to the first folder for data frames page views, and right there. So if you have any questions, just raise your hand and a TA will come and help you. So keep your hand raised. And I'm going to go ahead and continue, but somebody should be able to help you. When the TAs are able to be free again, just kind of raise your hand and maybe another 1 or 2 minutes, and then they can come and help you. So instead of keeping your hand raised, I would just wait like 2 minutes, let them help the other people, and then they'll come and help you out. So let's kind of think about what we're going to do with this data set by looking at the business questions first. So I'm going to make this a little bit bigger. OK, so there are some business questions that we're going to try to answer here. For example, how many total incoming requests were to the mobile site of Wikipedia versus the desktop site? What is the start and end range of time for the page views data? Which day of the week does Wikipedia get the most traffic? And then we'll actually do some visualizations as well. And in order to achieve the answers for these business questions, there are some technical accomplishments we will also have to do. So I'll just let you skim through this for a second. Okay, so introduction to running Scala in Databricks notebooks. It's pretty simple, really. Here is a Scala cell where we are setting the value x to 1 plus 7. If I do that, and I just kind of hit Shift Enter in that cell, then it gives me the output, so it executes that cell, and it moves my cursor to the next cell. Now, maybe I want to stay in this cell and not move to the next cell, so I can just hit, instead of Shift Enter, I can hit Control Enter, and you'll notice the cursor stayed in that cell. If I hit Control Enter again, it stayed in that cell again, perhaps because I want to edit it. But if I hit Shift Enter, it will not only run the cell, but move to the next cell. So this next cell is adding 2 to x and putting the output in the value y. And here we are printing out the value y. So this is not really Spark. This is just showing you a demonstration of running Scala code on the driver side of a Spark cluster. So none of this stuff is actually happening in a distributed way, not until we actually come down lower to start doing things with the SQL context. So a SQL context object is our entry point for working with structured data in Spark. And if I hit this, I can actually see that in Databricks, the SQL context is a shortcut for the Hive context. And what this means is that since it is a Hive context, it's more powerful. I can now have access to the more complete HiveQL parser, access to Hive user-defined functions, and I can read data from Hive tables if I want to. So what are we going to do here? Well, let's start by making a data frame called the page views data frame. And it looks like we're going to read in a table. So let me demonstrate how I uploaded the data to Databricks first. So this is perhaps something you might want to do later on this week. After class is finished, if you want to upload a data set, perhaps your data set is in Amazon S3. So what you'll want to do is you'll want to go to Tables. I actually already have this table created, so let me just show you what it looks like, and then I'll show you how I created that table. If I click on this, I can see the schema for this table has 3 columns, and there's 2 strings and 1 integer. And I can see some sample data here. So how did I create this table? Well, I went here, Create Table, and there's many options that we provide for how you can bring in your data. What I'm going to do is I will demonstrate how to pull in data from S3, which is perhaps one of the more powerful ways, because you can drop large multi-terabyte data sets in S3. So I have to provide my S3 key and ID and access key. Notice I can also connect to JDBC, relational databases, or I can actually upload a file from my computer if the data set is small enough. But I'll demonstrate the powerful technique of connecting to S3. So let me get my credentials here. And then once I put in my secret access key, I'm going to click Browse Bucket. Okay. Oops. That is my key. Let's do that. Bucket name is going to be so the bucket name is DB Wikipedia read only EU If I click Browse Bucket, I can now see the different data sets and folders I have here. I'm looking for page views. There it is. And there is a tab-separated file, the 255 megabyte file that we will be analyzing this morning. So if I click that and then I click Preview, then I can choose that this is a CSV file. I can choose that the first row is a header. And there we go. It has already inferred that this is a tab delimited file. And it's figured out that the first line was indeed the header, and it's extracted out the header names for the 3 columns. I can change this to integer. And I can change this to timestamp if I want to. But in this example, I actually left that as string to begin with so that we can actually cast that into a timestamp later on in the lab. But to really make this, all I would have to do is click Create Table. But since I've already done that earlier, I will not create another table right now. Instead, I'll go here and I'll click on the page views by second under my recent notebooks. Oops, not there. Right here. Okay, now I'm back in my notebook. So to begin my analysis, I need to create a data frame. This is structured data, as you saw. It's tab-separated data. And data frames is pretty ideal to analyze this type of data. So let's make a data frame called PageViewsDF. You'll notice that for readability's sake, I will try always to put the type of the object that we are storing in this value in the name of the value itself. So we know that we're working with the data frame right now. If this was an RDD, you would have seen the name be like this, kind of page views RDD. But it's not. We're making a data frame. And there we go. We can see the structure seems to have come in. So very easy to get started with working with structured data. Now, to begin with, I just want to get a sense of the data. I want to make sure the data got loaded correctly and is being parsed correctly. So I'm going to run the show operation. Okay, it looks good. In Databricks, we give you a helper function called display that does something very similar to show, but notice here now, instead of calling the show method on the data frame, which would work even in a REPL environment in your on-premise cluster, instead of that, I want to display this better. As you can see, I'm in a notebook environment. I have the full power of HTML here. So I'm going to run the Databricks display function to see it in a perhaps easier to read manner. And you can see that by default, Databricks only shows the first 1,000 rows. So even if you're working with a multi-terabyte data set, you will not overwhelm your browser. So I can scroll down and see a bunch more things now. I can also actually kind of expand this, or I can drag this thing or this little arrow around to make my table bigger or smaller. Print schema shows me the data types and whether a column can be null. So I'm pointing out something here that the first 2 columns are typed as strings and the request columns is an integer, which, timestamp should not really be a string. It should be a timestamp. But I did this on purpose just to show you how to cast things that might have been inferred incorrectly. So we'll fix that later. Now, there is something interesting I wanted to point out here. So look at what I'm saying here. If you go back a few cells up, it looks like we're missing some data. The first row is March 16, 2015 at 12:09 a.m. And the next row goes to 12:10. And I told you in the slide deck lecture that we have data every second. However, there seems to be a gap here. So let's go back and verify what I'm talking about here. Okay, so yeah, it looks like there is a gap. Well, the reason this is happening is because our data set, the 255 megabyte file we read, was actually, it didn't have the data in order according to timestamp. So it's not a big problem. We can just run order by timestamp column and then do another order by on the site column descending and then show the first 10 rows. So now it should show me all of the timestamps in order. So here we go. We now can, let me make this a little bigger so you can read it. There we go. Okay, that looks a little better. So I'm seeing mobile, desktop, mobile, desktop, mobile, desktop on a 1 second increment. My initial intuition tells me here, just by skimming this, that mobile site requests are less than desktop site requests in general for a given second. So perhaps there's more desktop requests that are currently occurring in 2015 than mobile requests. Okay. Well, our data looks good. I'm ready to do some analysis now. Okay, so let me scroll down and I'll make this a little smaller. There. So the first thing I want to cover is the power of using and leveraging the memory of your cluster with Apache Spark. This 255 megabyte data set is rather small. And if you read it from S3, it's not going to be too slow. Let's try it. I'm just going to call count on this data frame to see how many records there are in it. And what's happening right now is our Spark cluster, which is in Amazon EC2 in the Ireland data center, is reading data from S3 in that same data center. And I can see it took like 10 or 11 seconds to do that. It's not too bad, but I want to work at memory speeds. So I'm going to call the cache table command and pass in my table name. So I'm going to now cache this data set in memory of my own cluster. This is not going to happen on your cluster. So this is happening on my cluster right now, and you'll want to do the same thing with your cluster. Now, cache is a lazy operation. So running this command didn't actually cache anything, and I'm going to show you that. So if I click on this, I'm not going to detach from my cluster. I'm not done with my analysis yet. I'm not going to restart my cluster. I do want to look at the UI of my cluster. So this tab just opened up. I actually already had it open here, so I'll close that one. And now, this is like a best practice. When you're getting kind of started with Spark, or if you're actually trying to get deeper into how Spark works, I recommend having the Spark UI open so that when you run a command, you can see how it's taking effect in your cluster. So I'm going to go here and click the Storage tab, which will show me cached data sets in memory of my cluster. And you can see nothing shows up. Now, this is not to say that my cluster does not have access to data. As you already saw, we have access to that file in S3. The storage tab simply means it's, this should say like in-memory storage. And I'm not leveraging anything in memory right now. So you'll notice that even though I ran this cache table command, it didn't show up there, because cache is a lazy operation. It only will take effect the next time I need to read my data. And while it's being read the next time, it will also be stored in cache. So I'm just going to call the count action one more time. And now it's actually being read and counted and stored in memory. So if I now hit storage, it should show up in memory here in just a sec. Let's watch it come in. There we go. Well, it's not fully cached yet. It's only 25% cached. And that 25% is about 45 megabytes so far. It should be done by now, so I'll click this one more time. And now I can see that this data set, the page views by second, is in memory. And in memory, it's taking up 192 megabytes. So now that it's cached, let's call count one more time to see if we get better performance. Much better, less than a second. So now we can do interesting things with this data. So I'll answer perhaps the first like 2 or 3 questions with you, and then I'll let you do this lab on your own. I'll let you play around with this lab for about maybe 10, 15 minutes, and then I'll come back and run through the lab on here. So now what we're doing in the class today is exploratory analysis. We're not going to write 100 lines of Scala, productionize it, and then run it. Instead, we're going to play around with data. And this is the power of working in a notebook environment as opposed to an IDE like Eclipse or IntelliJ. So I'm going to start by filtering out on the site column just values equal to mobile and then do a count on that. Notice that in general, I have, how much data is that? Well, it's quite a bit. So what is that, like 7 million or so? Rows. Let's count just the mobile rows. Okay, great. So it's hard for me to read that actually. There we go. So that is about 3.6 million rows of mobile data. Now keep in mind, this is real data from Wikimedia Foundation. This is live data, not live, but live collected data. Okay, and desktop as well. So this makes sense to me. It is indeed what I expected. 1 row for mobile, 1 row for desktop, and they match. Okay. I can do something similar by running this command. I can group by site, call count, and then show. And this will show me the same thing, but now I can do both things in one command. Great. So 3.6 million rows of mobile, 3.6 million rows of desktop. Let's answer another question. How many total incoming requests were to the mobile site versus the desktop site? Remember here that each row is each row actually contains many requests. So I want to somehow know how many total mobile requests there were versus desktop requests in this data set. So to do that, I will go back down to my cell. Let's see. Let me refresh that. Okay, let me just hit page down a bunch of times and get back down there. Okay, we're still in memory. We answered the first question already. And now we want to do this. We want to sum up the request column to see how many total requests are in the data set. So I'm going to import some SQL functions here to use, so that I can use sum. And I'll sum the request column and hit show and call show. And well, this is how many total requests I have. That's quite a bit, as you can see, right? 13.3 billion requests. But the question we had was how many were for mobile versus desktop. So I'll give you the answer here. This is how you do it with data frames. We're going to filter on the site column, and then we will select out the sum of the requests column. And we can see that there's about 4.6 billion requests for the mobile site. So these requests probably came from mobile browsers. What about the desktop site? More, so 8.7 billion. So my intuition in the beginning of this lab is indeed correct. It appeared to me like there were more desktop requests. And when I look at the data set holistically, that does appear to be the case. So I'll do one more question with you, and then I'll let you kind of do this lab on your own for a little bit. Then I'll come back and I'll walk you through the rest up here. what is the start and end range of time for the page views data, and how many days of data do we have? So once again, remember what the schema of our data looked like. We're going to make a new data frame here called data frame 2. Okay, and we are selecting out the timestamp, casting it now correctly to a type of timestamp, aliasing that to timestamp as well, so it shows up again as the same column name, and then we're also selecting out site and requests. There we go. Now, this is also a lazy operation. Until we actually call some action to request the data inside page views data frame 2, nothing actually takes place. That's why that happened fast. So I'll print the schema, but this doesn't request the data either. So we haven't actually materialized the page views data frame 2. However, when we display it, now we're starting to materialize the next data frame. And now the timestamp column looks a little bit differently formatted because it is now correctly typed. And finally, the question we wanted to find out is how much data do we have from a time-based perspective? So I'm going to use some of these date time functions in Spark. So consider right-clicking on this, open this up in a new tab. And you might want to have these Spark API docs handy here as you go through some of the rest of this lab. So these are just the functions available in Spark, and you can see aggregate functions, and a little lower, those are the date time functions that we'll be using in the next few cells. Also, if you go here and type in data and then frame with a capital F, and click that. So anytime I'm operating on data frames, I always have this open in another tab so that I can see all of the different actions and functions I can call on data frames. You can also expand these to get a little bit more information and sometimes some example code. Okay, so let me go back. Okay, so how many different years is our data from? So I'm going to use the handy year datetime function against the timestamp column. And I just want to see distinctly how many years I have. Only 2015. Well, okay. How many months though? So instead of year, this time I'll call month. Distinctly, I will see that there are 2 months of data here, March and April. Furthermore, what if I want to see how many weeks of data? Weeks of the year is what I want now. So week 12 to 17, 6 weeks of data. And if I call the day of year datetime function, I can now also see that there are 41 days of data. Okay. Before I let you guys tackle the rest of this lab on your own, I want to show you some handy statistics functions. So here we're looking at mobile statistics, and we can see that in a given second, the minimum number of mobile requests was about 600, and the max was 3,000. Average about 1,200 mobile requests per second. Desktop statistics. More. Almost twice as much, right? 3 to 6. 2,500 on average per second versus 1,200. Okay, with that being said, it is about 9:50 a.m. here in Amsterdam. I will give you guys maybe about 10 minutes to go through the rest of this lab. Now, keep in mind that after today, we are going to give you access to the shard for another 30 days. So because of that, I would urge you not to get too caught up on certain syntax things, but get a sense of what's going on. Then you can hack on this lab on your own over the next 30 days. All right, so I will resume at 10 a.m. And I will then go through the rest of this lab so it gets recorded for the YouTube viewers. And then we will move on to something else. All right, and keep in mind, we will take a break at about 10:30. All right, good luck. Okay, so I had left off at question 4. And I assume that the rest of you have kind of taken the journey down this notebook, but I'm going to quickly run through it, and then we'll move on to something different. Okay. What day of the week does Wikipedia get the most traffic? Monday or Tuesday? Well, this is the command I'm going to run to do that. Once again, don't get too caught in the syntax if you haven't used data frames today, or before, I mean. It's okay, you can play around with this later. You're going to get so much sample code today that you'll probably have a lot of stuff you can do with this code later. So okay, this is what I'm going to run. I'm going to take my data frame, group by the timestamp, yank out the E is a pattern in the Java class that gets the day of the week, like Monday through Sunday. Pull that out, sum it, cache the data frame that comes out, assign it to days of the week. So let me run this cell. Well, that didn't work. Interesting. Well, so there is a feature in Databricks. What I can do is I can go to permissions. One of my friends at Databricks is Andrew, who's a software engineer who works on the Spark project. I'm going to give him, I'm going to give him full permissions on this notebook. Save my changes, and then I'm going to get the link for this notebook, Slack it over to him, and well, he kind of has already entered the notebook. I can see. So if I hover on top of this, I can see that Andrew's here. And let me scroll down, and I'm going to communicate with him via comments and ask him to kind of help me out with this. So, okay. So I'm going to go to the Comments tab. And, oh, that's what it was. Okay. I just needed a val here. And then I'm going to hide the comments again. Perfect. It looks like the cell is now executing. And we are now going to cache this new data frame that's being created. All right, so this is a technique you can use for the rest of the day if you need help in your notebooks from someone sitting next to you or someone who's not sitting next to you. Okay. Great, so I can see different days of the week. It looks like Monday gets the most traffic. Interesting. So it's kind of hard for me to figure out what's going on here. So one of the powerful features in notebooks is the ability to visualize, and in Databricks we have built-in visualizations. So I'm going to pass the data frame that just got created. I'll order it by day of the week, display it. It got ordered alphabetically, not how I wanted. So what I'm going to do now is, by the way, this has already been done, but you can actually move between tables to different types of visualizations. I will switch to the bar graph here. You can kind of see the different output. Okay, well, this doesn't look good. Friday, then Monday, then Saturday. I need a user-defined function to order my x-axis correctly. So here I'm defining a UDF, basically. Okay. So then I'm going to test it with the word TUE, and yes, perfect. Tuesday works. It's the third day, starting with the Monday being the first. And then I'm going to register my user-defined function. And then I'm going to call that user-defined function named prepend_number, which simply prepends it so that when I then, with the correct number for the day of the week, so that when I then order it and run it, I can see it gets properly displayed from Monday through Sunday. So that is one of the cool things you can do with Spark. Similar to other SQL-like projects like Hive, you can do user-defined functions. Okay, what's the next question? Can you visualize both the mobile and desktop traffic? Maybe with a line chart, so you can see them both. So this is the code that will help me do that. What are we doing here? First, graph the mobile site requests. Okay, so this is just for mobile, and I can see a max of, on Monday, of about 800,000. This is over the entire collection period of 41 days. Interesting. So it seems to kind of be steady for the rest of the week, but this spike on Monday is curious, isn't it? Well, let's continue and do the same thing for desktop. So for the 41 days that we collected data, let's see what it looks like for Monday. I mean, yeah, Monday, well, same thing with desktop. It looks like this is actually a pretty significant change, and I'm kind of curious what is going on here. And this is a pretty significant drop. Considering this is a top 10 global website, this fluctuation is quite odd. I'm kind of suspicious of it, to be honest. Okay. What was next? We wanted to look at them both together, actually. So what we're doing here is we are taking the data frame that has the mobile views by day of the week. Notice that it is a DF data frame. We're joining it to the desktop data frame on the day of week column. And perfect. And notice that here I'm choosing a line chart. Now, the thing that I don't like here is this is a little bit deceptive because my y-axis does not start with 0. It starts with 600,000. So actually there are quite a bit of mobile traffic here on the different days of the week, but this is a deceptive graph. So I'm going to switch over to a plotting library that's going to give me a little bit more control over the axes and other things like that. So let's switch through all of this. And notice here that with the %Python trick, I can switch over to Python within the Scala notebook. So here I'm just declaring a Python function called simple math that takes in 2 arguments and prints out what z is equal to. So let's see. Yep, looks like Python is working. But I want to use matplotlib, and I'm not going to cover how matplotlib works here today, but I'm just going to demonstrate some functionality. So here we're making a, let me make this a little smaller, a simple graph just to get things started. That doesn't mean anything. That's not made out of our data. And then I'm actually going to combine these 2 data frames into a, well, first I'm plotting, it looks like that's a desktop. Then I'll plot mobile separate. Okay, and then finally, I'm going to register them both as temp tables. And this cell, I believe, will actually make the plot that I want in just a second. Okay, so once again, there's just some boilerplate code to get to this graph. So notice here that I'm demonstrating essentially 2 plotting technologies. You can see that actually using the Databricks built-in visualization is much easier, but perhaps a little bit more limited than using these sophisticated plotting libraries like matplotlib. So this looks better. The y-axis problem has gone away now, but this is still bothering me that desktop is, and mobile traffic is so much higher on Monday than on the rest of the days of the week, and I just don't trust this. So I'm going to show you something. Remember, we're doing exploratory data analysis here, and I actually tricked you. We didn't explore our data quite enough to catch what was going on. I'm going to now do something at the bottom. Okay, let me make this bigger so you can see what I'm doing. Let me just go and do this first. Okay, so I'm taking my page views data frame. This is the one we made much earlier in this notebook at the very beginning, grouping it by timestamp, yanking out the day of the year, and summing it and ordering by requests that came in on that day, and I'm showing all 41 days. Now, notice here that this day, let me make that bigger so I can read it. Okay. Hang on. So this is why exploratory data analysis is important before you productionize your jobs. Well, let's see. If I look at all this data, let's just kind of look at this data. We're looking at 41 days of data by day. But look at this outlier here. The 110th day of 2015 saw a lot more traffic than all the other days, which are pretty stable. So it's curious. I don't know what's going on here, but every other day, it's like I don't know what that would translate to, but that 3 number, except for the very last column, the very last row. So what is the 110th day of 2015? April 20th. I'll leave this exercise to you to figure out what's going on there. All right? But what that is, by the way, well, actually, I'll go a little further. Notice that this is actually a Monday, April 20th. Is the 110th day of the week. If you go into one of these things, maybe here, events. Well, okay, Google's probably not the best way to figure this out, but look at your calendar for April, what April 20th is. At least I know it's April 20th now, and April 20th is a Monday. Now notice this was 6 weeks of data, so if 1 out of 6 of my collections is off, that could skew my entire analysis. So that seems to have been what happened here, right? Our data set was quite small to begin with. It was only basically we're doing it by Monday or days of week. That means seven different x-axes, right? So that's kind of what happened. Like that one day is throwing off everything else. Okay, so I just wanted to point that out. And we are done with this lab. Let's move on to something else. Now, we will take a break in a little bit at 10:30. But before that, I would like to cover data frames for about 10 minutes. We'll take a break. When we come back, we'll tackle a different data set and do some different things with it. Before I talk about data frames, though, another show of hands, how many people here have used data frames in any language, like Python, Pandas, or R, or Spark? Wow, okay, so that's like 80% of the people, and that's great. That's kind of what I was hoping, that you guys had played around with this before. So let me quickly cover data frames and how they kind of work. We're looking at the actual page views data frame here. So the way I like to visualize data frames is kind of like this. Our specific page views data frame is actually made of 4 different partitions. If I go to the Spark UI, I don't need these 2 tabs anymore. Remember that data frame that we put in memory has 4 partitions. So we just read it in, and it somehow became 4 partitions. How did that happen? I'll explain in just a second. But the way to think about a data frame is it's basically, well, it's storing the data in different partitions, and these different partitions could live on different executor JVMs in your cluster. In this class, I've given you a small local mode cluster. So you really have only one JVM, and I'll explain the architecture of that JVM later today. But in your case, these different partitions are not on different machines, but in a real-world data set, if this data frame was significantly larger, like 10,000 or 30,000 different partitions, you can imagine those 30,000 different partitions, each one being on perhaps different machines. I can see that my columns in a data frame are typed. They're typed as, timestamp or string or integer, and also the columns have a name, like time or site or request. And I can get the size of the data frame by just running df, like the data frame name, like page views df, and then .rdd. So I convert my data frame actually to an RDD, then call the partitions method, partitions.size method on that. So why 4 partitions, though? This was a 255 megabyte file. Well, the way it works when you read data from Amazon from Amazon S3, I should say. So that should actually say S3, not EC2. When you read from S3, which is where our 255 megabyte file lives, by default, Spark reads the input split in 64 megabyte segments. Therefore, a 255 or so megabyte file divided by 64 would give us about 4 partitions, basically. So that's kind of what's happening. So you can now imagine that if this was like a 1 terabyte file just divided by 64 to see how many partitions will be in your initial base data frame when it's read out of S3. Different input data sources will do this differently. So if you're reading from HDFS, for example, every block in the HDFS file will be read into its own partition. So if your HDFS blocks are 128 megabytes, each 128 megabyte block will give you 1 partition. A year ago, the way Cassandra was configured, for example, Cassandra, which is a NoSQL database, if you read data from Cassandra into Spark, 100,000 rows in Cassandra would give you 1 partition. Every data source treats this differently. So when you work with a new data source, first learn how that data source will give you the different partitions. How will it segment off that data set into the different partitions? All right? Now, the other thing I wanted to cover is the logical processing model of a data frame. So when we have S3 up here, and we do the SQL context read, we then get the data frame with 4 partitions. And then remember, we did perhaps a filter and a count. This was like the first operation we had done way in the beginning of this notebook. Let me scroll down just a bit to the filter, then count. So where is it? A little further. I think it was the first question. Yeah, here. So look at what I'm doing. I am on the data frame just running a filter and a count. And I want to start understanding now a little bit about what's going on behind the scenes. So to go back to the slide, when we read in a data frame and then do a filter and a count, logically, perhaps what you're thinking in your brain is you read the data frame initially, it has all the data, then we're filtering it out to just the mobile traffic here. We got rid of all the desktop data, and then we did a count. However, the way this actually runs in Spark, the physical model is different. This is how it runs. So we have S3 at the top, and then when we do the initial read and filter, we use 4 different threads or tasks to do that, and then we do an aggregation with a count, and then we get the 3.6 million. So the way this looks like actually in Spark is like this. So how do I interpret this, and where do I get this from? Well, all will be revealed in time. I'm not going to go too deep into this. I'm just going to show you where I got that visualization from. But first, what I'm going to do is I'm going to come here to my UI. Remember, I got this by going here and right-clicking on this and just opening up in a new tab, and then I would come here. Here, there's 44 jobs that ran while I was exploring my data here in this notebook. Now, notice that the last job that ran is this job ID 43, okay? So now I'm going to come here and I'm going to run this command, which should kick off job ID 44. There we go. Job 44 should have run now. So let me refresh this. And now, wait, did that run? So let me do that one more time. Okay. I'm not sure why that didn't get updated. Okay, let me see if I can just go and find that command, though. Okay, I'm going to scroll down. Oh, there it is, actually. It's kind of, okay, so it's all the way at the bottom. It just, there it is. Display. So these are all the jobs. Maybe I can just find one of the old ones by going down here and finding that job. Not the count, but we did a there it is, okay. Okay, this is a job that is basically this one from like the first time I had run it. So what am I going to do here is I'm just going to click on this, details for the job, and you can hit this DAG visualization to see that graph. And when you work with data frames, this graph is a little bit harder to understand, so I'm not going to explain it right now. I will just say this, that this is a job with two stages. There's stage one that pipelines all of these different operations, and then we have a shuffle boundary. This is like an all-to-all shuffle happening. Then we do the count. Okay? So for now, just keep in mind that this job was somewhat computationally expensive because, and network expensive because I did this shuffle. And I'll explain kind of more about what's going on here when we go to the RDD land, because it's easier to understand these diagrams in RDD land. The other thing I just wanted to show at this point, though, is something else. It's really good to always know how many tasks were launched, how many threads were launched to accomplish your job. And the way I'm going to read this here is I start with the lower stage. So this stage 19 ran first for half a second or so, and it ran 4 tasks, 4 threads. This stage, the first stage, 19, remember, this is all about this one cell. Okay, we're going behind the scenes to see what happened. It kicked off 2 stages. In the first stage, it read 192 megabytes. This is actually the storage data frame. Remember, the data frame was 192 megs? We read that using 4 tasks. They all succeeded. Why 4 tasks? Because the data frame is 4 partitions because of what I explained earlier, 64 megs each. The next stage that does the count ran for very little, 7 milliseconds, and it read the shuffle data that this stage wrote out. So notice that the shuffle right column here and the next stage read the shuffle data. All right, that's really all you really need to understand at this point. The fact that we have figured out that that cell has a computational cost of 4 threads, 4 tasks. They're pretty fast, and I can kind of understand the shuffle that happened between the 2 stages. Everything else is something we'll cover later. Now, the thing with data frames to keep in mind is that it is really the most ideal way to analyze your data. When you use data frames, whether it's in SQL or R or Python or Scala, you'll get the same speed in any language, because we are going to take your code, run it through a Catalyst optimizer, and then run that code natively in the executor JVM. In this example, by the way, we're aggregating 10 million integer pairs, and we can see how long that takes in seconds. If I do that using RDDs in Scala, it takes like a little bit more than 4 seconds. RDDs in Python don't run in the executor JVM. UDFs in Python run in Python PIDs next to the executor JVM. I'll explain all of this when we talk about architecture later, but the only main point I want to make here is data frames will give you, when you use data frames, whether you're using R, Python, or Scala, you'll get the same speed because it's being run in the executor JVM. Okay. And we will take a coffee break in just a second, but I thought maybe it'd be interesting to tell you guys a bit about yourselves. So we did a pre-class survey that was mailed out to you guys, and I just wanted to show you the results of that, of one of the questions of that. So of the 100 or so people here, about half of you guys submitted the pre-class survey as of like midnight last night. So how experienced are you guys with Spark? You fall between level 2 and 3, which means you guys have written a few hundred lines of Spark application code. You understand the technical details of what kind of transformations in the world of RDDs can cause a shuffle. And a lot of you guys have been using Spark for more than 50% of the time for the past 2 months. There's no Spark committers here, though, or maybe one person contributed some source code to Spark. One more thing. What stage of Spark adoption has your team reached? So the first one was still exploring Spark versus other big data projects. That's maybe 20% of you. A lot of you fall into here. You're building either a proof of concept prototype, or you're starting to take your first Spark application to production. Cool. And a lot of you, maybe 10 or 15% of you are actually already in production, and now you're looking to do optimizations. This is great. This is probably the ideal audience for this class. So I feel like I can skip over all the basics, and I'm just going to keep moving into some of the more technical depth. But it is exactly 10:34 right now. Let's say it's 10:35. Let's take a 20-minute break. So that means that we are going to resume 35 plus 20 at 10:55. So please be back at 10:55. There's a pretty packed day here today, and I would like to make sure I can cover as much of the material as I can. So if you can be back in 15 minutes, that would be great. So I can start exactly at 10:55 without any interruptions when I'm speaking. All right, I'll see you guys in 15 to 20 minutes. All right, guys, let's go and get started. So what I'm going to do next is we're going to talk about Spark's architecture for maybe about 15 to 20 minutes. And then I will show you how to look at Spark's architecture using the Spark UI. And then we'll move into one of my favorite data sets for today, which is the clickstream data set. Okay, so Spark's architecture, more specifically how it relates to your class today. So as you saw, there is a notebook that you guys have been using. Now I'm going to reveal what's going on behind that notebook. Essentially, in Amazon, there is an EC2 machine with approximately 60 gigabytes of memory. And in that machine, there is a container inside which there is a JVM, and that's where we are running a local mode Spark cluster, which means that we've embedded the Spark driver and the executor both together in this cluster. This is kind of like a prototype cluster. It's not really meant for large production scale jobs, but you can still get pretty far in it. And another student might be on the same EC2 machine as you, but just isolated in a different container. And inside these containers are slots where tasks can run, up to 4 in parallel at the same time. And you can now also see that this container is about a 30 gig container, and the actual JVM is a 21 gigabyte JVM. Okay, so since we're running in the cloud, this is what the classroom looks like, right? There's a whole bunch of EC2 machines and notebooks connected to them. So let's zoom in to this one a little bit. By the way, when we cache an RDD or a data frame, that gets cached inside the JVM itself. Okay, so I want to zoom into this and take a closer look at just the JVM and focus on Spark. So remember, there is a container that this JVM is in. And what I have done here is, okay, so we have an RDD, let's say, or a data frame that has 4 different partitions. This is actually the page views data set, right? But that was a data frame. This is an RDD. Now, to process this RDD in this example, what we need to do is we're going to take the data from here, move it in to the slot, and then run a thread there, a task. And we actually need to process 3 more partitions, so let's do that. And in the JVM, there are more than just your 4 user threads. There are many others. There's like 15 or 20. They're used for things like shuffle, garbage collection. They're usually in a thread waiting state, but they're there as well. And your notebook is connected essentially to this JVM. When you run cells in your browser, the cells are sending the commands to be executed inside of this JVM. Now, this is how it works when you use Scala. But if you use Python, then what we do is in the container, remember it was a 30 gig container, 21 gigabyte JVM. In the container, we have some Python processes running as well. This is what gave you that trick in the lab to be able to run Python as well. These Python process IDs, they, I believe, get something like 512 megabytes of memory each. And there's also a Python driver which actually just connects back to the normal Java driver. So when you use PySpark, your notebooks are connected to this Python driver, which is like not really a Spark driver. The Spark driver is still living in the JVM. We just, this is like a Spark driver controller, and the driver is still there. So they're connected like that. Now, when you process Python UDFs, they process in these Python PIDs. And since Python is a dynamically typed language, because of the inherent nature of Python, it's just a little bit slower than running things at native speeds in the JVM using Scala or Java. So this is processing Python UDFs. If you process Scala or Java, you use the thread, you run threads in the JVM itself. Now, the cool thing with data frames or running SQL commands in Spark is that regardless of which language you use, data frames or SQL queries always get processed at native speeds in the JVM. This is why data frames are the ideal way to process data in Spark. When you call MLlib, or the machine learning library in Spark, once again, we always run at native speeds in the JVM, regardless of which language you're using. And talking about languages, I thought maybe I can show you guys the results of the pre-class survey for languages. What is your level of experience with the following technologies? So everyone knows SQL. You guys seem to be more of a big data background, perhaps, because you have a Java background, most of you. You're starting to learn Scala, and you're not really data scientists with a lot of R experience. Like I anticipated, you guys are more big data people, maybe with the Hadoop background. So you can see kind of the breakdown of the different languages here. And actually, a few months ago at Databricks, we ran a survey, that was this summer in 2015, to identify insights into how organizations were using Spark. The results you see here reflect answers and opinions from about 1,500 respondents and from about 850 organizations. So you can see that Scala is the most popular language out there to use with Spark, with Python coming in second place. In general, I would recommend you to use Scala, because the source code in Spark is Scala. It might be a bit of a tougher language to learn, but I can guarantee you the trade-off will be worth it in the long run for you guys. I also wanted to mention that there is a new R&D project underway in the Spark community called Project Tungsten. This is going to be the largest change to Spark's execution engine since the project's inception. It focuses on substantially improving the efficiency and memory, the efficiency of memory and CPU for Spark applications. And the goal of Project Tungsten is essentially to push the performance of Spark closer to the limits of modern hardware. One of the ways we do this is we, instead of caching RDDs and data frames in memory, we now will be, in the near future, starting with Spark 1.6, caching them off heap. And this uses java.unsafe, and we will then manually manage the memory. And we will prevent garbage collection from occurring more often in the JVM by doing this. So if you're interested in learning more about Project Tungsten, there's a lot to Project Tungsten. I would recommend perhaps Googling Databricks blog Tungsten, those 3 words, and you'll come across a really in-depth article about the architecture changes happening to Spark Core. Project Tungsten will not change really the user-facing APIs of RDDs or data frames. What you will notice is simply when you upgrade to Spark 1.6 or 1.7, when we turn on all of the Project Tungsten features, you'll simply notice your Spark application has sped up perhaps by a factor of maybe even 2 or 3. Okay, so I will not get too deep into Tungsten right now. I just wanted to point it out. What I will get into though right now is the clickstream data, one of my favorite data sets. So this is a larger data set. It's about 1.2 gigabytes in size. And I initially discovered this data set when I ran into a blog post by Ellery, who is a data scientist at the Wikimedia Foundation. And it was this beautiful diagram about the London article in Wikipedia. And the clickstream data is created using referral resource pairs. For example, the Google referred someone to the London article. Actually, Google referred something like almost 50 or 40% of the traffic to the London article. And it looks like some other Wikipedia pages also referred people to the London article. I can actually interpret this diagram to mean that when people come to the London article, when the 100% of people come, it looks like only maybe like 15 or 20% of them click on a link inside the London article to move on to perhaps the England article or the UK article or the City of London. And then it goes, less and less people go to some of these other articles. So this was a cool diagram, and actually the way this is made is not by a just refer resource here, but actually for this side, London becomes a referring article to the resource of England, for example. So, we're in Amsterdam today, so I thought it'd be cool to make this for Amsterdam. So that's what we will do in the next lab. But let me introduce you to the data set. it's 1.2 gigabytes. Once again, a tab-separated file. Data frames or SQL would be the ideal way to analyze this structured data. We have 22 million referral resource pairs out of 3.2 billion requests to Wikipedia in February 2015. This data is just for the desktop version of English Wikipedia. This is what the data looks like. In the lab, we are going to create a data frame called the clickstream data frame. Once again, you can see I kind of put the type of the data in the value itself, in the value or variable name itself. So this is the referral resource. Resource is under the column named current title. Referrer is under the column previous title. The way I read this is that Google referred to this article title 121 times. If the request came from a Wikipedia article, then I get the Wikipedia article ID. And since we're looking at Wikipedia requests, I always have which Wikipedia article was requested, the resource itself. Right? So you can see all these double exclamation marks, which I'm not really sure what that means, but if you scroll further down here, you would see more human readable article titles. Here, though, you can see that all of these are the same article title, therefore they have the same ID. And you can see the different sources that send data to that. And remember, this is a subset of the data we're working with, so don't fall into the same trap that perhaps the first lab tricked you into falling into, because it was only 6 weeks worth of data. So what do I mean by refer? Right, this thing? This column? Well, the referrer can be Wikipedia. So if it says, if it has the actual article title in here, like here it has the article title, right? Loudon up now. That is actually a Wikipedia article. I'll show you. Where did it say Loudon up now? So let's go look at that. Loudon up now. I'm not sure what that is. But notice here, Loudon up now. Capital L, U, and N. Same thing. Okay. So I get the article title if the referrer was from the main namespace of English Wikipedia, meaning most likely another article. It says other Wikipedia if it came from a Wikipedia page, but it was not in the main namespace of English Wikipedia. What is a namespace? Wikipedia namespace. Here are the different namespaces in Wikipedia. In this class, we're going to mainly focus on namespace 0. That's where the articles live. Now, there's a lot of other things in Wikipedia as well. Let's look at the Amsterdam title article in Wikipedia. This is also in the main namespace, but you'll notice here that there is a talk page. What does this mean? This takes us out of namespace 0 to a different namespace. And this is where basically people can talk about, talk and debate about how they want to change something in this article if it's being contested by somebody else. This is the debate behind the article. Oftentimes on contested articles, the talk page will be significantly larger than the article itself. So the talk namespace is, which one? Namespace equals that 1. So namespace 1. But anyway, we're going to focus on mainly the 0 namespace where the articles live. So let's click on that. And you can read more about what's in here. There's actually more than just this article. This namespace has, as you'll see later when we actually work on the 50 gigabyte snapshot of Wikipedia, there's actually a little bit more than just articles here. So we'll have to remove them before we actually do our third lab. But for this lab, let's continue looking at what the referrer can be. It can also be any page from any other Wikimedia project, like Wikidata. It can be a search engine, send data to the Wikipedia article, a social network, or empty referrer means that we don't know. This is usually HTTPS traffic, encrypted traffic, or anything else for something we can't interpret. Okay, so what about the N column? This is the number of occurrences of the refer resource pair within our time frame. Remember, our time frame was February 2015. So 1 month's worth of data, and a subset of that month at that. Okay, so we know what N is. It's how many times that referrer requested that resource or pointed somebody to that resource. What about type? Well, type can be one of three values. It can be link, if they were both just articles and one of them linked to the other. Remember, this is clickstream data. This is not just a link. This is like somebody went to one of these places, like went to Google, searched for something, and then went to that article. Or somebody went to London, searched, then inside London they clicked on a link. Then in that case, London would become the previous title, and the link they clicked on inside the London article would become the current title. Okay, so this is also explained in the lab further. This is actual data where you can download it. So I just figured I'd show you that all these data sets are publicly available. If you want to do this on-prem in your own cluster, you're more than welcome to. So the question I thought we could maybe answer is, what does the traffic inflow versus outflow pattern look like for the Amsterdam article? It would actually be really nice to visualize this using the Sankey diagram that I showed you that Ellery made about the London article. But maybe it'd be cool to show you how to do that for any article that you want. So what we will do is I'm going to do the same thing as before. I'm going to essentially walk you through maybe like the first 20% of the next lab. And then I will let you hack on the lab for a little while. Then I'll come back and kind of walk through the YouTube audience through the rest of the lab. So once again, I need to go back into my own directory. Remember, you'll do this in your own home directory. So I'll go into my home directory, and under labs, I want to go to, remember, if you go to table of contents, just so you know, if you click on the lab for clickstream through here, then you'll get to like a static copy of it that will actually be in the labs folder. So the table of contents for all of you points to this labs folder. That's not what you want if you want to edit and mess with this lab. To edit this lab and play around with it, you'll need to go into the private repo, the private repository of this lab that each of you has individual copies of, distinct copies of. Then I'll go to the second lab. And once again, I want to find the run me one without any output. Okay. If you have output in your cells and you want to clear the output, that is doable. You'll notice here, for example, there is some output there that I would rather it not be there so that only the cells were there. So I'm going to show you a trick to get rid of the output. All right, so I'll go here, more tools, developer tools, click on console, and then you can actually type stuff down here. And I'm going to copy and paste this little function for clear results, and then I'll run it. This is what I typed in. I'll leave that there for about 10 seconds if you want to write this trick down. This just clears all the output cells. And then when I run through this lab, I won't see the results until I hit Shift Enter or Control Enter. Okay, so I'm going to attach this to my second demo cluster. which is a freshly restarted cluster, so I won't have to do that again. And I'll let you skim through some of the questions we're going to be trying to answer here. What are the top 10 articles requested from Wikipedia in February 2015? Who sent the most traffic to Wikipedia in that month? What were the top 5 trending articles on Twitter? So we're going to try to reverse engineer the answer to this by seeing which articles did Twitter send traffic to in Wikipedia. What are the most requested missing pages? So that's interesting. We're trying to find which articles people tried to get to, but they didn't exist. And then we'll make the diagram. So maybe I'll cover the first 3 questions, and then I'll let you do the lab on your own. We will break for lunch probably right around 12:15. So that's about 1 hour from now. If we can, I'd like to do it at noon. So let's see if we can get to it maybe a little earlier. So we're going to do a little bit more now. We're going to use the Spark CSV library to read structured files. Then we're going to join data frames. We'll actually intermix SQL and data frame queries seamlessly. This time, instead of using Databricks native visualization or Matplotlib, we'll use a third visualization technique, Google visualization. And you can get to Ellery's blog there, or you can get to the raw data. Okay, I don't need to bother with the restart. Okay, so there's a helper function in Databricks called dbutils that lets me print out what is in this directory in S3. So I just want to make sure the data is there. Yeah, there it is. And the size is 1.2 gigabytes. So I can go here, byte to gigabytes, 1.3 gigabytes. Okay. So we will use the Spark CSV library to read this data. It makes it very easy to read structured data, and you can learn more about it here on the GitHub page. How did I know that this even existed? There is a new community website that was launched earlier this year for Spark called Spark Packages. This is a really cool website, and it can save you a lot of time. And what it is there's 141 packages right now, and it's growing every day. For example, if I wanted to read comma-separated value files and I couldn't find a feature to do that in Spark, I might come here and type in CSV and realize that there is actually a community package called Spark CSV that lets me read in data from comma-separated value files that's very highly rated by the community, actually. So it looks like it probably works fine. So this code is not part of Spark and has not been reviewed by the Spark committers. Essentially, Spark is moving very fast. It's the fastest moving open source project, I believe, in the entire Apache Foundation. And what we did is we made this packages page so that anybody in the community can just submit code for Spark. And there's like things to read data from Cassandra, for instance. You can also look at just graph packages. Now, this code has not been reviewed, but you can kind of figure out how good the package is based on community ratings. And I would encourage you to submit your own packages if there's little things that you wrote that are perhaps useful for the rest of the community. Okay, back to our lab. I'm going to make a data frame now, called it clickstream data frame. You can see that in the Spark CSV package, there's a bunch of things, extra parameters you can pass in. Once again, we're not going to get stuck on details today. We're just going to move fast and get the bigger picture. Okay, so I make my data frame. I always like to display it to make sure the structure looks like I anticipate it. Okay, that looks good. Let's scroll down a bit. Okay, this looks good. So we're looking at the Heroes article. Oh wow, so from this David Bowie album, from this article, people a lot of times, 2,600 times in February 2015, clicked on, in this article, they clicked on the link for Heroes. I can probably find it. So if I go there, come here, wiki. Now this is the page. And here, if I search for heroes, that link, let's click on that. Let's see if this, well, that's not the exact same link. It actually went all just to heroes, so maybe I need to keep going. Let's find the next one. No, that link doesn't look like it's the right one either. You know, it might have also been changed. This is February 2015. Now Heroes is sending us to this page. So this got updated. It was originally going there though, which is probably a different article. So the thing I like about working with Wikipedia data is I can kind of do this and I can kind of start linking the data to like this. So, interesting. This is like a page with a whole bunch of things that can refer to hero. All right, that's how you interpret this data, though. Let's look at the schema. That should have been an integer, not a string. Same thing with n. So let's fix it. Right, so you can see what I'm doing there is selecting out the previous title and the current title. That's all I need. I actually don't need the ID titles for my analysis right now. So I'm only selecting out the titles that I need and casting the n to an integer. And I'm pulling out the type as well. So 4 columns are being pulled out. In this next data frame, clickstream df2 that I created right there, you'll notice I've pruned out the first 2 ID columns that are unnecessary for me. And I casted that correctly to an integer. Okay, so I'm going to skip through this part that explains the data. We already did that in the lecture. Count how many rows we have. Not only am I counting to understand how many rows there are, but I'm trying to understand the cost of reading this 1.2 gigabytes from S3 into my local mode Spark cluster. So count scans through the entire data set. Show does not. Show will stop once it's gotten enough data to display the, in this case, 5 rows. That's why this ran much faster. However, when I do a count, it does actually have to get to the through the entire data. So, okay, it looks like it's going to take about 45 seconds or so. And I should see that there's about 22.5 million rows or lines in here. So what I always like to do is have a UI open for my cluster. So I'm going to get into the best practice habit of doing that again. Okay, my count is probably still running. There it is. You can see it's under active jobs now, not completed jobs. And it's going to require 21 tasks to go through. And if I click here, I can perhaps go to DAG visualization. And once again, I'll kind of reveal what's going on in this visualization later. But I can see it's at least 2 stages, and there is a shuffle happening between 2 stages in this. Okay, there we go. All right, so I definitely want to cache this so that it will run faster. And remember, cache will, oh, look at what I did. I called cache and then count right away to go ahead and force the cache to be implemented this time, right away. So I don't really care about the results of count. I already got that up there. I'm just trying to trigger the cache to happen right away instead of happening lazily later on. So it will take another 45 seconds to read this data into memory. It's probably being read right now. It's this one right here. And in memory, it will be probably close to about 500 megs. Okay, so what are we doing next? I guess as soon as that cache finishes, we will run count one more time to see the speed increase of operating on a gigabyte of data in memory versus doing remote reads from S3. Keep in mind our local mode cluster is in the same Amazon data center. I believe both S3 and the cluster are in the Ireland data center right now. That was the closest we could get to Amsterdam. Okay, so I'll keep going through this for about maybe 5 or 10 more minutes, and then I'll let you guys hack on this lab yourselves. Okay, so now how much faster it is? Much better, less than a second. Okay, what are the top 10 articles requested from Wikipedia? I'm going to get some results and then put the whole thing inside the display function. Actually, get 10 of the results and put that in the display function. But you can see that I'm basically taking the clickstream data frame, grouping by the current title that's being requested, select out the current title, and the sum, order by the sum, descending. All right. Cool. So the main page of Wikipedia, which makes sense, I guess. I guess Academy Awards were happening in February 2015, and maybe a new 50 Shades of Grey book was released. We can run the same command with SQL. So I'm going to register a temporary table, which is only going to be accessible through my cluster. So you'll need to do this for yourselves, for your clusters. Call it clickstream. And then just test it out by selecting all the columns from clickstream and limit it to 5 results. Looks good to me. Then this is the SQL query to do the same thing as a data frame query. So let me run that. So now you have the option to either use data frames or SQL, whichever language you are more comfortable with. Both of these queries, SQL or data frame, are going through the Catalyst optimizer and generating the same physical plan. So you can choose your language of choice. Cool. So here's some other things you can do in Spark SQL. Notice that I'm using this %SQL to switch from Scala. This cell now is being switched to be a SQL cell. I earlier did the trick with Python. Now I'm doing it with SQL. I'm just describing the clickstream table there, which has 4 columns, and I can see the types of the columns. SQL has a bunch of functions, and the show functions command will show you those functions. Cool, a whole bunch of nice helper functions. Great. We can also use explain by, to understand the physical plan of the SQL statement. All right, so that's that. And I won't dive too deep into what's going on there. I'm just trying to give you a wide coverage of Spark. Notice that in Spark SQL, this is not a relational database, right? So you're never going to be able to do updates or deletes. This is essentially, even though it's SQL, it's not for low latency transactional databases like the use case of MySQL or Cassandra. This is batch analytics, right? This is kind of like Hive. So updates and deletes are not supported. Okay, next question, the next business question. Who sent the most traffic to Wikipedia in February 2015? So I'm going to group by the previous title, the referrer, sum that, order by the sum, descending, show the top 10. Google, I guess that would make sense. Other empty. Other empty is usually HTTPS traffic. And then other Wikipedia articles. So Wikipedia seems to be sending people to a lot of other Wikipedia articles. One interesting thing is that Twitter sends 10 times as much traffic as Facebook. I don't know, perhaps Twitter is a more intellectual community. What were the 5 top trending articles on Twitter then? Once again, I'm not going to dive too deep into what's going on here, but I will show you a trick right now. So if you want to understand what's going on with data frames, one thing you can do is to decompose this statement, first remove, this is how you can learn data frames. This is how I learn data frames. I'm going to remove the display completely. And then what I can do is just get rid of all of this. I want to understand what the filter does. So I'll just do filter limit to 3. Oops, I have a typo. All right, so this is what I would recommend you to do if you're not too familiar with data frames, and then grow this slowly. Okay, I understand, okay, limit 3, and then do a show 3. Well, I don't need to do a limit anymore, actually. That was only for the display function. Okay, so I know what filter does, but what else did I do here? A group by? So what does a group by do? Okay. See, so then I'm going to, okay, so group by, See, the group by is returning grouped data, and group data is not a data frame. That's why I couldn't do a show. But on group data, I can do a sum. All right, so I won't do this. I want you guys to play around with this on your own. I'm just trying to show you a little trick. And then that gives me a column called sum, and that doesn't look good. It's a weird column name. I'm going to, well, I guess I left it here, but you could change the name to something more readable if you want. I didn't do that in this query. Anyway, well, what was the question? What were the top 5 trending articles on Twitter? There we go. Johnny Knoxville was famous on Twitter, perhaps. He was up to his pranks or something in 2015, February. Same query in SQL, actually, so if you prefer SQL. All right, so you can kind of, if you want to learn how to move between data frames in SQL, feel free to look at those 2 cells more closely later on. Okay, at this point, I'm going to let you guys hack on this lab for a little bit, and then I will come back and quickly run through this lab. So it is 11:35. I'll give you maybe 10 or 15 minutes to run through the rest of these questions. And remember, once again, just kind of move fast. The point is here to give you a tour of the different engines in Spark, not to teach you little tiny details. All right, so you have about 10 minutes. Okay, let's go ahead and get started. Okay, so I'd left off in question 4. What are the most requested missing pages? Now, this is an interesting one. This is how I do it. Let's select distinct from clickstream. So here, you see the red link? A red link means that if the refer is an article and links to the requested, but the requested is not in the production English Wikipedia table. Let's find the most popular red links, meaning a lot of people were looking for these articles, but they did not exist. Huh. So you can see a bunch of data. Let's maybe just look for one of these and see if it now exists or if it still does not exist. So I'm just going to find the Wiki Amsterdam article again, then I'll edit the URL. So what would happen? Maybe it shows up by now. Yeah, so I mean, that's what you would do, and that's how you could check if one of these articles is currently there or not. Okay, so that's a cool way, I think, to, if you want to contribute a new article to Wikipedia, that's perhaps how you can find articles that not only could you create, but they would probably then be read. What does the traffic inflow versus outflow look like for the most requested pages? Traffic inflow versus outflow. So first, let's find page views per article. Looks good. I'm selecting out just 2 columns, the current requested article and how many times it was requested. Okay, what's next? Then find the link clicks per article and show the top 10. Okay, so this is a referrer that had an out count of this much. So we're building up to something. So let me just kind of keep moving here. Join the 2 data frames we just created to get a holistic picture. And then this should now start making sense. Interesting. So we joined on basically this and this. In count, out count on the main page. On the alive page, incoming, outgoing. It looks like on the alive page, people don't like clicking on anything to continue. I wonder why. Okay, well, yeah, it's not like even a real article. So they end up there, and then they're like, close tab. So we're going to also add a ratio column to understand the in count versus out count ratio. And this will make more clear what I just said about the Alive article. But on Alive, let me make this bigger so it's easier to read. On Alive, you can see in count. A lot of people went to that article, but nobody leaves. But on 50 Shades of Grey, it looks like at least 50% of the people continued onward onto other Wikipedia pages. Okay, we're almost ready for lunch. What does the traffic flow pattern look like for the Amsterdam article, and create a visualization for this? So we're going to, from that data frame we just made with the ratio, we'll filter it out to just the Amsterdam article. Curious here. So yeah, the ratio is not too bad. 35% of the people continue from Amsterdam on to something else. This means that, yeah, maybe I do want to make a visualization. Because if this said like 1%, I would probably not want to make a visualization. Because if that said 1%, what that means is that for the people who came to the article, 1% of them clicked onward. So the visualization would be almost meaningless. But this looks fine. 35% of people continue onward from Amsterdam. Okay. Which referrers send the most traffic to the Amsterdam article? Let's see. Google and the Amsterdam airport. Netherlands article. Well, it's hard for me to really try to understand what's happening here. It would be much nicer if I could get this in a visual way. So I'm going to run this command. I guess up here I ran a SQL command to do that from the clickstream data or the clickstream table. You can do that with data frames as well, and I'm just demonstrating the same thing in data frames. Okay. Which future articles does the Amsterdam article send most of the traffic to? So they get to Amsterdam, and then where do they go? Show me the top 10. Kingdom of the Netherlands and a bunch of places. What Amsterdam is famous for, I guess. So anyway, I do want to make a visualization for this. So I'm just going to run this cell here. I'll quickly tell you what's going on. We're basically, I've hand-coded all of these here, But actually, in a future lab, you'll learn how to programmatically do this. So I'm basically calling this display HTML function. And then I won't go through all of this, but that's calling a Google visualization. And ta-da, here's what we get. So if you can see that the weight here is much higher than the weight there. And now it makes more sense. And looking at all those tables, which like I was looking at them and I was having a hard time interpreting what was going on, but now I can see that only some people who come to Amsterdam click onward. A lot of people mainly come from Google, almost like 70 or 60%. Cool, so I'm going to conclude by doing a couple of things. First of all, when we come back from lunch, I'm going to go a little bit deeper into explaining how Catalyst works. But here, when you do explain on a data frame, it shows you the physical plan, the computational plan for running that. And when you do explain true, then you can get the logical plan, and at the bottom, the analyzed logical plan, and way at the bottom, I believe, is also the physical plan. Optimized logical plan, and then further onward would be actually the physical plan. So there is a physical plan. So we'll come back to that after lunch. However, I thought maybe I could give you some food for thought before that. So here's what I have for you before lunch. A Spark demo. Maybe one of the first YouTube videos ever on Spark. This is a YouTube video from June 2011. This video was uploaded by Matej. Matej Zaharia is the creator of the Apache Spark project, who is currently a professor at MIT and also the CTO of Databricks. And in the comments of this video, this is what Matej typed up. On disk, 20 seconds, in memory, 1.2. It's a really short video, so why don't I play this for you? And notice that when I play this video, this is Spark 0.0. So let's see what he does. I mean, he actually didn't have any audio when he recorded this. So, but let's see if you can interpret what he is doing. I'm going to make this full screen. Actually, let me open this up in a browser window. So this is a very rarely visited video. It had, how many hits? Under 2,000. So like nobody really found this ever, but this is perhaps the original video showing the world how Spark works. What else can we see here? Matej uses a Mac. OpenJDK. Okay, so anyway, let's see what he's doing. Let's see if you can figure out what he's doing. He's at the Spark shell. He's doing 1+1. SC text file to read a file from S3 Wikipedia tab separated file. Then he's pulling out the first record in the file. It looks like a XML. He's making a class object for articles, title, string, and then value text. Then he's on the file RDD. What is he doing? .map, split on tab, and then filter for something that actually has some content. Now he has the articles RDD, and he's filtering that. RadLab. This was the precursor to AmpLab. So this is like the original department at UC Berkeley where Spark was born, and then the RadLab was then, it became AmpLab. So he's looking to see how many mentions there are. It took 18 seconds to read that TSV file from disk, and he did find one article, I guess one mention of it. And then he's making a new data frame called cached from the articles, and then he's going to do the same scan. He's probably only doing this because he needs to move it up into memory. He'll get the same result here probably. Okay, almost done. So those are task IDs, I believe. Okay, so now in memory, instead of 21 seconds, on disk, in memory, it's about 1.5 seconds. So what's he doing now? RadLab, title, collect. Which article was it? The title. David Patterson, scientist. Interesting. What is he doing next? He's making a new RDD called, no, he's making just a string basically called Berkeley. Contains query. How many articles? 11,000. Ooh, his competitor school there. So who is more influential in his Wikipedia data set? Well, it looks like Berkeley wins there. But he downsampled the data set, and I'm not sure what technique was used. But that's really it there. It is just about exactly noon. We will resume exactly 1 hour from now at 1 p.m. So please try to be here like 5 minutes before if you can, so we can get started right on time at 1 p.m. And then we will actually hack the full Wikipedia corpus at that time.